Okay, we're going to introduce kinetics. This is brand new to you guys. I don't think you studied any kinetics last year in first year chem. So our first section is reaction rates. So, by the way, kinetics will be the study of rates of reaction. So there is a definition. Rates. We could call that speed. Rate is anything that's measured over a period of time. It will typically be molarity, so these will be solutions generally, but they don't have to be. And so again, rate, in this case reaction rate, and it could be in context of reactants. And reactants are going to lose concentration over time. And then products would be adding, increasing concentration over time. And if we look at delta, and delta, that's change. So these are going to give us average rates. So give you a context of that. So if you go from Pittsburgh to Philadelphia down the turnpike, you get there in a certain amount of time, and you could have an average rate. I don't know what the distance exactly is from Pittsburgh to Philadelphia, but that distance divided by time would give you an average rate, an average speed. But that whole entire time from point A to point B, you probably had many different speeds. So we could look at an instantaneous speed, maybe at some point, hopefully when there was state cops around, you were under the speed limit. But then other times, who knows, maybe you were over the speed limit. And but the average speed very likely was going to be well under the speed limit. So this is about all you might have studied last year in first year chem. If you didn't, no worries. But these are different things that can influence rates. Make rates go faster, make rates go slower. And certainly these are a case-by-case basis. They don't always have the same effect. But if you have more concentration of reactants, typically the reaction will go faster. As you have less and less concentration, the rate slows down. Again, these are general ideas. They're not 100%, and they're not always the same. They're a little bit different reaction to reaction. Typically, if you raise the temperature, it will make the rate go up. Surface area, if there's more places for these molecules to run into each other, the reaction will proceed faster. Sometimes catalysts can be involved. We'll talk a little bit more about that. And probably we won't get too much into environmental factors, but there's other things that could make reaction rates also increase. Here is a typical graph of a chemical reaction. So this one looks like it's 2N2O5 going to O2 plus 4O2. And we could, look at the graph, but we could also look at the chemical reaction. And by looking at the chemical reaction and the graph, we can kind of piece things together. Yes, there was a key given to us over here, but we didn't really even need the key. So I know that we have 2N2O5 as a reactant, coefficient in a reactant. Reactants have to lose material over time. So this has to be the line that deals with the reactant. You have to lose reactant over time. Now that slope, I know it's a curve, but there'll be instantaneous slopes, there are tangents. If you look at those, the one I just outlined, it starts to level off over a period of time. That means as the reactant concentration goes down, the reaction proceeds at a slower rate. But those rates have to deal with the coefficients, the 2 to the 1 to the 4. If we would look at the two products, they should start off at 0 because you have no products at time 0. And they don't go up at the same amount. It's hard to tell with a curve, but this is the coefficient 4 compared to the coefficient 1. So this is for the NO2, and this is for the O2. So they should go up by different rates, by different. Again, you're not going to get a straight line per se with these curves, but you could look at a tangent. That's a straight line off of the curve, and they definitely will be different. So what I just mentioned here is this. I know that looks a lot more confusing, but it's relating how you would get rates for the different reactions. And you do notice that the reactant has a negative there. So often we can actually use the negative, but we can also use words to describe the negative. So lots of people will say rate of disappearance of N2O5. And all that means is that you don't have to worry about any positive and negative signs because you're using words to describe that. And I'd say actually that's more typical for people to use the words as opposed to the signs. So I did mention to you that we could also, at any given point in time, also have a rate. And if you look at this graph, it's curved. So with a curved graph, the rate continually changes. At the 0 for the x-axis, that's the fastest the rate will ever be. And then as the reaction proceeds, it's going to slow down, slow down, slow down, slow down, slow down. You can't see it on this graph, but at some point it will approach leveling, going horizontal. So that brings us to our next one. So we could have done average rates, and we had visited that a slide ago, but now we can also look at an instantaneous rate. If you wanted to know the instantaneous rate at 600 seconds, right there. Whoops, let's bring that up just a little bit. You would need to get the tangent of that. Now, there's computer programs that you can actually do that with, but we'll talk about how we can mathematically do that too. And that tangent is going to be significant for us. Why? Because that will be an instantaneous rate. So we had an average rate we mentioned, and now we have an instantaneous rate. And we're going to get to this in a second too, but we're going to come up with an equation. I'm just going to rewrite it differently than what it's written here. Rate equals K. What the heck is K? K is going to be a constant. This constant is going to be unique to every particular chemical reaction. It's not unique to the amount used in that chemical reaction, but it's unique to particular chemical reactions. And then we're going to have, in this case, it says reactant here, but we don't know exactly how many reactants are in the chemical reaction. We also don't know what this could be up here. Since there's nothing up there, that means it's a 1 for this one, but they're not always going to be 1s like that. But anyhow, this is going to be something called a rate law. And we're going to get to that in a second here. But all I need to show you with this graph is that we could do what we did in the last graph and get an average rate, but we can also get an instantaneous rate. And the instantaneous rate at like 600 seconds is going to be much different than like at 200 seconds. 200 seconds, that slope is much more severe than at 600 seconds. So this is faster here, and this is slower. Okay. Okay, so that looks awfully confusing there, and it's not nearly as confusing as it looks. So we have a reaction, generic, and what are these capitals and what are the lowercase? The capitals are the chemicals. Chemical A plus chemical B makes chemical C plus chemical D, and then the lowercase are the coefficients. So this is going to be kind of difficult to kind of look at, I believe, but this is the way it was written in your book, so I decided to put that in there. And all it does is show you how the coefficients relate to all of the other coefficients as far as rates of reaction. If you know one of the rates of the reaction, you know all the other rates of the reaction. And so instead of really wading through this, let's look at one of these questions, and I think you might see that this is a lot easier than it looks. So the rate for oxygen looks like 0.024 molar per second. So that is for that chemical right there. If I wanted to know what's going on with N2O5, I could figure that out if I know the coefficients in the balanced chemical equation and what's going on in O2. So in O2, it is 0.024 molarity per second, and then the relationship between the chemical N2O5 and O2 is a 2-to-1 ratio. So all we have to do, whoops, I was going to put a 2 there, that's not right. So for N2O5, it's going to be 0.048, 2 times that value. And I'm not bothering with any signs. I know there's a sign, the rest of them have positives, because it says what was formed. If it didn't say rate of event, if it didn't say something about used up or formed, then we would have to use signs. Okay, so now let's try to figure out NO2. To do any chemical in the chemical reaction, we have to know one of the rates. We could either go back and use that rate, or we could use the rate for O2. Let's just keep what we were doing before. So let's start with the O2. And then what's the relationship between O2 and NO2? It's a 4-to-1. So all we got to do is multiply this by 4. Okay, and we probably, it doesn't say anything about, well, it doesn't say rate of disappearance. So I probably should put a negative in here. Or I will actually use words. Rate of disappearance. Okay. Okay, next question. So we have a chemical A, and it had a certain molarity. And then at 125 seconds later, it has a new molarity. So what's the average rate? But it doesn't ask about A, it asks about C. Well, we can't do C until we do A. So how are we going to do that? So we have to do the change in concentration. Whoops, that's not a very good line. Let's do that over again. And then divide that by the change in time. and we start at 0. So you could have just left this at 125 seconds if you had preferred. And when you do that subtraction and the division, round that to this is the disappearance for A, and if I don't want to use numbers, I could just slap a sign in there of a negative. Now if I wanted to do C, C is just going to be 3 times 1 of that value because it's a 1 to 3 ratio. So for C, rate of C, it's going to be not a negative this time because it's a product, and I'm just multiplying it by 3. And there we go. If I wanted to look at B or D, I could have done that also, but it just didn't ask us that in that question. And I think that's all we got. So that's a little introduction to kinetics.